Hello, students. So, you've just finished learning the statement and proof of the comparison test. And the long story short version of the proof of the comparison test is monotone convergence. What we're going to do in this packet is prove two results which you will also remember from calculus. We are going to be proving the root test, and we won't prove it in this packet, but it will be relegated to a homework, like a bonus homework walkthrough that will have you prove the ratio test. And both of these have a proof that can be summarized by stating two ingredients. So the proof of both of these are just use comparison with a geometric series. That is, both of these proofs will have one main step which will contain most of the walk. So let's hear the statement of the root test. So the root test says three things, but I'll focus on the first one. If the limit superior of the sequence given by taking kth roots of the absolute value of ak, so notice there are two k's, so that's not the sequence ak, it's not the square root of ak, it's the kth root of each ak. If you take the lim sup of that, limit superior, and you get something less than 1, then the series converges absolutely. If you take that same lim sup and find it to be bigger than 1, then the series diverges. And here's the structure that the convergence one will use. So the first thing we'll do is we'll use the fact that lim sup absolute value, lim sup of the kth root of absolute ak is less than 1 to show that there exists a constant r such that, well, maybe I'll write it this way. The kth root of ak, absolute value bars, for all k, not for all k, is less than r, is less than 1, provided k is big enough. And then what can we do? Well, we want to get rid of that kth root. We want to understand ak itself. So we'll do exactly that by raising both sides to the kth power. So we'll get that conclusion, provided k is big enough. Oh, hey, but check this out. Then this thing converges. It's a geometric series. And eventually ak is less than r to the k. Well, if eventually ak is less than the terms of a convergent series, then we'll be able to use by comparison test, we'll conclude that the sum of ak converges. And that's the sketch of the proof. That's how things will go. So let's put rubber to road and prove the root test. There's also another result called the ratio test, which theoretically is a strictly weaker theorem in that there's a proof of the ratio test that just uses the root test. Let ak be a sequence of positive numbers. If you take the lim sup of the sequence of ratios of successive terms, and you get something that's less than 1, then the series of ak's converges absolutely. If you take the lim inf and you get something that's bigger than 1, then the series ak diverges. And the proof will be for you of that one. So let's prove the root test. So proof of theorem 2.10.4, the root test. Let the sequence let AK be a sequence, and assume that the limit superior of the sequence of kth roots of the absolute values of AK is less than 1. So that's the assumption of part 1. There's the hypothesis. AK is a sequence, and you get to assume this. We want to show that the series converges. I guess it already has absolute value bars in it, so this absolutely is redundant. As alluded to in that sketch of proof off to the side, we will do so by comparing the series to a carefully chosen geometric series. So I need to manage to pull that off. So let's try to do it. So we'll just use what we know about lim sup. So let's let L be the limit superior of the kth root of a to the k. I'll suggest that you pause this lecture really quickly and go and review the reformulation of limit superior in terms of epsilons. That is to say, theorem 2.6.7. I think I'd rather highlight. Review this theorem in the notes. So pause right now, go do that and come back. Okay, good, you did it. So you know that L is a subsequential limit of this sequence because the limit superior, right, it's the supreme of the set of all subsequential limits. But one thing you know about the limit superior is that it happens to be a subsequential limit. The other thing you know is this line. For every epsilon bigger than 0, there exists some big N, which depends on epsilon. So I'm encoding the dependence by saying n of epsilon, so that whenever little k is bigger than that threshold value, big N, the kth root of AK is less than L plus epsilon. Right, so the terms of the sequence can exceed the limit superior, but they can't exceed it by very much for very long, is what that says. No matter how... For every little error term you want, there's some threshold, so that as long as you look after that threshold, that should be n of epsilon, be consistent, then the sequence is less than L plus epsilon. All right, so by assumption, L is bigger than 1, so we can probably get something that involves like 1 minus L to be bigger than 0. Maybe there's a hint here about what I'm going to wind up dividing by. So, but I'll leave that blank for now. So I'm going to play this game where I'm going to decide which epsilon I need to use. So I can come up with something bigger than 0 that comes from the fact that L is less than 1. Sorry, I just had to sneeze. So let's consider any little k bigger than that choice of big N. I'll need to figure out what goes in that space. So by our choice of n, then, we can conclude that the kth root of AK is less than L plus whatever we want to put right here. So this thing will have the job of epsilon, and there is that same epsilon, which is a thing that is less than 1. So, well, let's figure out what would do the trick then. I want to put some quantity here, which turns out to be less than 1. And, well, let's try to do that. So L, this is a side. Maybe I'll do it in yellow. Let's figure out what goes in those blanks. Let's see, L plus something over 2. I need that to be less than 1. So let's figure out what we can put in that blank. So looks like we want question mark over 2 to be less than, subtract L to the other side, 1 minus L. Oh, neat, but 1 minus L is positive. if I take 1 minus L and divide it by 2, I get something that's less than 1 minus L. So maybe I'll put in this blank 1 minus L. So let's go ahead and insert that. So I'll start reading here. By the assumption, L is less than 1, so that means that L minus 1 divided by 2 is bigger than 0. So what does that mean? That means I can take this line, which I know to be true for every epsilon. I can take that as my choice of epsilon. That'll give me a choice of big N dependent on that epsilon. 1 minus L. So that's big N of 1 minus L over 2. By our choice of big N, we now have that this kth root of the absolute value of AK is less than L plus that choice of epsilon. 1 minus L over 2. And let's just go ahead and simplify that. So L plus 1 minus L over 2. Well, do the algebra yourself. You will get L plus 1 over 2. And I assert that that is less than 1. And on the one hand, here's an intuitive way of seeing that. That's the average between L and 1. That's the number between L and 1, so that should be less than 1 because L is less than 1. But maybe here's the intermediate step you could use to do that. So that's something less than 1 plus 1 over 2, which is equal to 1. Yeah, so that number is less than 1. So if I set R to be that quantity, L plus 1 over 2, I now have that for all K, I think I want to insert a little bit right here. If we set if I set that to be the choice of R, I now have the kth root of absolute AK is always less than R, at least as long as K is less than our choice of big N. So AK itself is less than R to the K, at least for all K, again, greater than big N of 1 minus epsilon over, bigger than big N of that, L minus 1 over 2. All right, well, now I'm basically done. So this is the type of inequality you need to use the comparison test. If I know that the series of all of the RKs converges, then I'll be done. Do I know that, though? Well, yeah. Absolute value of R is less than 1, so the geometric series formula says that the series associated with the RKs converges. In fact, it tells you what it converges to. And I think I myself will pause and take a moment and check that this setup satisfies all of the hypotheses of the comparison test. So I'm going to scroll up and look at the comparison test. Just the statement of the comparison test. So it's that AK and BK be sequences of numbers. In this case, AK will be exactly the same as the thing that we want. As we have right now, it'll be AK. So I'll take this to be the AK we have. This BK will be R to the power K. I need this inequality to be true for all little n bigger than or equal to this threshold value. So this threshold value will have the job of, I guess, big N of this epsilon, I don't know, maybe plus 1. Because as soon as little k... Oh, that was a typo. I wonder if it was fixed already. As soon as little k is bigger than that threshold value, big N, I have this inequality. Moreover, I know that the series of all of the R to the k's converge, so I can conclude that the series associated with the AK's converge. Nice. So that's... So that was that pause to check. We now satisfy all of the hypotheses of the comparison test. So by the comparison test, the series of all of the absolute AKs converges, and so by the definition of absolute convergence, the series of AKs converges absolutely. That's just what absolute convergence means. Nice. So there's half of the proof done. The other half of the proof will be super straightforward. We'll just use the divergence test. So let's suppose, on the other hand, that lim sup of AK is strictly bigger than 1. I want to show that the series associated with AKs diverges. By the test for divergence, pause, take a moment, go and check what that says. Good, you did that. By that theorem, if we want to show that the series of AKs diverges, I just need to show that the sequence, AN or AK, doesn't matter which you call it, but I should be consistent. I need to show that that does not converge to 0. So here's what I'll do. I'll use the fact that the lim sup of the kth root of AK, I'll use the fact that that is bigger than 1. Well, the lim sup is a subsequential limit, so that will give me a choice of n sub k's, or I guess k sub j's, so that this happens. Well, I guess as long as I'm outlining exactly what's being written, I may as well just read along. Since L is a subsequential limit, in this case, of the sequence of kth roots of a sub k's, it follows that there exists a strictly increasing sequence of natural numbers, a bunch of k sub j's. So the limit as j goes to infinity of the k sub jth root of a sub k sub j, so all of the k's are now k sub j's, is equal to L. And I know that that number L is bigger than 1 by assumption. Neat. So I have a subsequence a sub k sub j in mind. I'm going to show that a sub k sub j does not converge to 0, because if a sub k sub j does not converge to 0, that certainly means that the whole sequence can't converge to 0. And, well, if the whole sequence doesn't converge to 0, then the divergence test concludes that the series diverges. All right, well, let's put that together. So since L is bigger than 1, it follows that a certain thing is bigger than 0. I don't know. Previously it was 1 minus L, but this time L minus 1 is bigger than 0. So eventually I won't put this there. I'm leaving my space intentionally. So it follows that L minus 1 is bigger than 0. So let's try taking that and having that be the thing that has the job of epsilon in the statement that the limit of the kth root of a sub k sub j converges to L. So it follows that for all little j bigger than big N, the k sub jth root of the absolute value of a sub k sub j minus L is strictly less than L minus 1, though again, I'm leaving space because I'm not going to want that to be what goes there eventually. I want to explain why that means that the k sub jth root of a sub k sub j is bigger than, actually bigger than or equal to would do just fine. Let's use bigger than or equal to. In fact, maybe I won't have to do any changing. Let's explain why that means that this quantity is bigger or equal to 1. Well, neat. So let's just try to do it. I guess that means I want to solve for this quantity. So you know what I'm going to do. Whenever you see an absolute value less than something, that means, so because absolute value k sub j root of a sub k sub j minus L is less than L minus 1. I'll leave myself space in case I want to change it. We conclude that negative L minus 1, so 1 minus L, is less than the thing in the absolute value bars, the k sub j root of a sub k sub j hope there should be absolute value bars. I don't know if there were on the previous one. Minus L is less than L minus 1. All right, fair enough. Well, let's take that and solve it for a sub k sub j. Thus, so I guess I want to subtract L from everything in sight. Thus, we get 1 is less than absolute a sub k sub j, but kth rooted, k sub jth. Not enough space. K sub j root of absolute a sub k sub j is less than, I'm adding L to the other side, so I'll get 2L minus 1. Oh wait, but the first thing is exactly what we need. In particular, the k sub j in particular the k sub jth root of absolute a sub k sub j is less than 1, as we desired. Oh wait, but there's an obvious simplification we can make to that. Like, if the k sub jth root is less than 1, then the thing itself must be less than 1. So by raising both sides to the k sub jth power, the absolute value of a sub k sub j is, I goofed there, didn't I? Oh, wait, so if that inequality is true, okay, so I didn't get a less than or equal to, I got a less than. Thus, if the limit of absolute a sub k sub j exists, it is, no, let's phrase it this way, because that's not what I'm directly interested in. If the limit of a sub k sub j, let's call it a, exists, then absolute a is bigger than 1. So in particular, a is not equal to, bigger than or equal to 1. All right, if you like, I'm taking the limit of both sides of this to get that inequality. In particular, that means a cannot be 0. So we found a subsequence which does not converge to 0. It follows then that the whole sequence does not converge to 0. So by the test for the divergence, this series diverges. That completes the proof. So there are two things that I want to do with these two results. Because an important part of results like this that you remember doing from Calc 2 is using these results to prove that some series converge or diverge. So let's prove first that the sum from k equals 0 to infinity of k divided by 3 to the k converges. And we're going to use the root test. And I'm going to make one secret assumption. I'm going to assume that the limit as k goes to infinity of the kth root of k is equal to 1. And in fact, I'm going to, I'll explain to you why that's true, though the argument is just a Calc 2 argument. It'll use L'Hopital's rule, which we haven't justified in this class, as we haven't talked about derivatives. But I think this is worth going through as a tangent. So let's use what you remember, L'Hopital. And right, the reason is a bunch of algebra. So let's see. Let's just expand out k to the 1 over k. That's the same thing as e to the natural log of k times 1 over k, which is the same thing as e to the ln of k divided by k, as ln of k goes to infinity and k goes to infinity as k goes to infinity. L'Hopital's rule says that the limit of ln of k divided by k is equal to, take the derivative of both sides, the limit of 1 over k divided by 1 equal to the limit of 1 over k, which is something that you know, it's 0. Thus, the limit of k to the 1 over k is equal to the limit of e to the ln of k divided by k is equal to e to the limit of ln of k divided by k by continuity, which is something that we will talk about, is equal to e to the 0 is 1. So there's why. That's not content associated with the class, but it's something that's good to remember, though. You already knew it from Calc 2. Let's use that to prove that this series converges by using the root test. If we're going to use the root test, then we need to compute the limit superior of the sequence of kth roots of the terms of the sequence. Notice the terms of the sequence are all positive, so I don't need to worry about absolute value pairs. Well, if the limit exists and we can compute the honest-to-God limit, then we'll know the lim sup automatically. So let's do that. So let's compute the limit as k goes to infinity. That is the same thing as the limit of the kth root of k divided by the kth root of 3 to the k. So I guess the kth root of 3 to the k is just 3, right? By some cancellation. And we wind up with the limit of the kth root of k divided by 3. And then by the given that the limit of kth roots of k is equal to 1, this is just 1 over 3, which is less than 1. So let's just put the summarizing bit in. As we've computed the limit of the kth root of k divided by 3 to the k and gotten 1/3, it follows that the limit superior is also equal to 1/3, which is less than 1. So by the root test, that series converges absolutely, but it's already all positive, so that's the same as it just converging. Absolute value pairs won't change anything. Now, we didn't prove the ratio test, but let's prove the same result using the ratio test. So let's just remind ourselves what the ratio test says. The ratio test says if you have a sequence of positive numbers and you can show that the lim sup of the sequence of absolute values of ak plus 1 divided by ak is less than 1, then you will conclude that the series converges absolutely. All right, well, let's do that. So to use the ratio test, I need to compute this lim sup, because this lim sup is the k plus 1 term of the terms of the sequence divided by the kth term. And let's just do a quick sanity check. Is that actually correct? Look at the thing on the bottom. Yeah, that's exactly the kth term of the series. The thing on the top. Yeah, that's exactly what you would get out of this if you replace k by k plus 1. So that's what we need to compute if we want to use the ratio test. We will do so by computing the honest-to-God limit. So let's compute the limit as k goes to infinity of k plus 1 divided by k. K plus 1 divided by 3 to the k plus 1, all over k divided by 3 to the k. And, well, we'll just have to do it. So that'll be the limit. I don't know, so this is just like an algebra thing that you always know to do. Whenever you divide by a fraction, you should multiply by the reciprocal. I'm alternating and recording these videos between videos for my analysis class and videos for my pre-calc class. And so sometimes I'll, it's nice to see overlap. So I guess this is by what? This is by multiplying, well, by the reciprocal. And if you like, that's just true because A inverse is equal to A. All right, and I guess we can even simplify some right here. That's the same thing as the limit of k plus 1 over k. In fact, let's simplify that a little bit farther. Well, maybe we'll even just stare at this for a second and see if we think we win. So what's the limit of k plus 1 over k? Well, I guess by L'Hopital's rule again, but I don't want to use that too many times given that we don't actually know that rule. The top goes to infinity, bottom goes to infinity, the derivative of this is 1, the derivative of that is 1, so this piece goes to 1. This is k theories, k plus 1 theories, so this is just 1 over 3. Let's just do that same thing without that reference to L'Hopital's rule, and I'll do it instead by distributing this division. So that'll be the same thing as 1 plus 1 over k times 1 over 3. And I still need to write the word limit. I haven't evaluated the limit. But what's the limit of 1 over k? So because the limit of 1 over k is equal to 0, this is the same thing as 1 plus 0 multiplied by 1/3, which is just 1/3. So let's write the same concluding sentence. As we've computed this limit and gotten it to be 1 over 3, it follows that the limit superior of the same thing is 1 over 3, which is less than 1. So by the ratio test, this series converges. That seemed pretty okay? Cool. So that concludes this lecture. There are a few homework problems that I'm proposing for you on this one. One of them is an application of the comparison test to prove the p-series test, which in some sense is, well, it's another good result to know. And it will amount to just another well-chosen comparison, this time with a correctly chosen telescoping series. And I'll also have you do another application which will seem a lot like these. I'll have you prove that another series converges. And then, as I said, there's going to be this bonus homework problem in which I will have you prove that, I'll have you prove the ratio test. And there's even a little bit of a sketch of proof that I've provided. Great. I hope you guys are enjoying this pre-recorded format of lectures. This is all done well in advance, so hopefully it continues to work out well once I start bringing in the discussions that I want to have. Talk to you later.